Hello everyone, welcome to another video lecture for Octal 206 Microcontrollers with Lab. In this video lecture, which is for the lecture number 2, the second part of the lecture number 2 indeed, we are going to see how we can convert between different bases. In order to convert from one base to another one, we can do it in this way indeed. We convert the integer part separately. We can convert the fraction part separately as well. And then we can combine these two using a radix point. So let's see here how it is done for different parts. Regarding the integral part, it's kind of easier. For the integral part, we need to repeatedly divide the number by the new radix and then save the remainders. The remainders will be important for us. Then the digits for the new radix are the remainders in the reverse order. Okay, so this is important. In the reverse order, we will take the remainders and then we will put them one after each other in order to get the equivalent number for the integer part. If the new radix is bigger than 10, then we need to convert all the remainders bigger than 10 to digits, which are represented by A, B, C, and so on and so forth. We will see examples for converting into hexadecimal for this. And in order to convert the fraction part, we need to repeatedly multiply the fraction by the new radix and then save the integer digits that we get as the result. The digits for the new radix are the integer digits in the order of their computation. So we multiply the fraction by new radix, we get a new number. If the new number has an integer part, indeed it has, whether it's 0 or anything, we will take this and put them in the order of their computation. And if the new radix is bigger than 10, then we will convert all integers bigger than 10 into digits A, B, C, and so on and so forth. Let's see how it is done by checking it through an example. In this example, we are going to convert 46.6875 in base 10 into its equivalent in base 2. The number which is provided for us has both integer and fraction parts. So we can do it one by one. Let's start with the integer part. So we have 46 as the given number. We need to divide it by 2. What we get is equal to 23. And then we will have 46 here. The remainder that we get here is equal to 0. So we need to keep this. And then we continue division. 23 divided by 2 will give us 11. And the remainder that we get here is equal to 1. Then 11 divided by 2 will give us 5. 10 will be here, and then we will get 1 as the remainder. And we continue 5 divided by 2, we will get 2 here, and 1 as the remainder. And 2 divided by 2 will give us 1 and 0 as the remainder. And at this point, since 1 is smaller than 2, we will stop. And then as we just mentioned in the previous slide, we will use the remainders in the reverse order of their computation. So the last remainder that we will get will be used first. So we will have, starting from here, 1, then 0, 1, 1, 1, and 0. So for the integer part, we will have 46 in base 10 is equal to 1, 0, 1, 1, 1, 0 in base 2, or in binary. Then we have the fraction part. For the fraction part, we have 0.6875 as the fraction part. We need to multiply it by 2 by the radix. We will get 1.375. So the integer part that we have here will be important. And then we just drop that integer part, continue with 0.375 and multiply it by 2, which will give us 0.75. So this 0 will be also important. And then we just drop 0, which will give us again 0.75 multiplied by 2 will give us 1.5. And then we drop 1 and we'll have 0.5 multiplied by 2, we will get 1.0. And then since we ended up with 0, we'll stop at this point. Because if we continue multiplying it, we will get 0 all the time. And then for the fraction part, we will take the integer parts that we get here as 1, 0, 1, 1 in the order that we have received them. So 0.6875 in base 10 will be equal to 0.1011 in base 2. 1011 is the order in which we received the integer parts. And then we just need to combine this. As a result, 46.6875 in decimal will be equal to 1011.1011 in binary or in base 2. And then we can check out whether our conversion is correct or not. Assuming that we have the decimal number, we can find the equivalent. We have the binary number, we can find out the equivalent decimal number, and it should be equal to 46.6875. And I hope you remember how to do it. Yeah, we will have a plus sign here. For the fraction part, what we need to do is to multiply each digit. So 1 will be multiplied by 2 to the power of minus 1. 0 will be multiplied by 2 to the power of minus 2. 1 will be multiplied by 2 to the power of minus 3. And finally, 1 will be multiplied by 2 to the power of minus 4. And then for the integer part, the first digit will be multiplied by 2 to the power of 0. Second one will be multiplied by 2 to the power of 1, and so on and so forth. And then if we obtain the equivalent decimal number for the integer and fraction part, you can see that they are the same as the original number from which we just started to do the conversion. We can do the conversion directly from octal to the binary and back. So something to keep in mind here is that when you want to convert a given number like n from a base to its equivalent in another base from R1 to R2, you can follow the exact way that we have here. So for the integer part and for the fraction part, you can follow what we have explained here. But you just need to keep in mind that doing multiplication and doing the division in bases other than base 10 will be challenging. So for base 10, we can easily do the multiplication and the division. So it's something that we have learned from the school, yeah, from our early years. But if we want to do it for bases other than 10, it will be a bit challenging. So you need to pay extra attention when you do the multiplication or division in different bases. As a result, instead of directly converting from base R1 into base R2, one can do like this. So from base R1, we can find out the equivalent number in base 10, and this should be done easily, and then we can convert it into the equivalent number in base R2. So you can see that base 10 here will be used as an intermediate base to convert from R1 into R2. For example, if you want to convert from base 16 into base 2, we can do the same. We can find the equivalent number in base 10 and then find out the equivalent number in base 2. So that's the general indeed approach. However, for some cases, we have a special case. For example, when we want to convert from base 16 to base 2, since 16 is equal to 2 to the power of 4, there's a relation between these two numbers, the direct relation between the two. And it makes it easier to do the conversion. This 4 here means that each digit in hexadecimal, every single digit in the hexadecimal form, could be expressed with 4 digits in the binary form. And we will see how to do this in the over the examples in detail. So we can do the conversion in both ways, from base 16 to base 2 or from base 2 into base 16. From base 16 to base 2, each digit, like AI, will be expressed as let me call it maybe BI3, BI2, BI1, and BI0. Okay, so 4 digits will be used in order to express a single digit in the hexadecimal form. And this is two ways. So we can start from binary and go to the hexadecimal, or start from hexadecimal and end up in the binary form. And this also holds for the octal numbers. For the octal, we have the base as equal to 8, which is equal to 2 to the power of 3. So in the case of octal to binary and back, every digit in the octal system will be expressed with 3 digits in the binary, and vice versa. And now we will see how to do this. So we would need to create, when we want to do it from binary to octal or hexadecimal, we would need to create groups of the binary digits. For octal, we would need to create a group of 3 digits, and for hexadecimal, we would need to create groups of 4 digits, and then convert them group by group in order to obtain the equivalent number in the octal or hexadecimal case. Okay, now let's see it through an example. Okay, let me give you an example for this, and then I will move to the next slide where we can do the conversion from octal to hexadecimal via binary. Let's say that we have A0 in the hexadecimal and we want to find its binary equivalent. As just mentioned, for each digit we will use 4 digits for the binary. So 0 in hexadecimal will be represented by 000 in binary, and A in hexadecimal, which is equal to 10, will be represented by 1 0 1 0. And as a result, for the binary case, we will have 1 0 1 0, then 0 0 0 0. Okay, so you can see that it is quite straightforward. It's even easier than converting hexadecimal into decimal and then decimal to binary. As for the octal number, let's say we have 7.65 in octal and we want to find its equivalent in binary. So each digit in octal will be represented by 3 digits in binary. For 7 we will have 1 1 1. So therefore we'll have 1 1 1 dot. For 6 we will have 1 1 0 1 1 0, and for 5 we will have 1, 0, 1. So 1, 0, 1 will give us the equivalent number in the binary or base 2. To convert back from binary to each one of these, we will just use we will create groups of 3 or 4 digits in it. Let me give you an example. So let's assume that we have 1, 0, 0, 1, 0, 0, 0, 1 in binary, and we want to find its equivalent in hexadecimal. So here we have only the integer part. We need to create groups of 4 digits like this, and then represent each one with a single digit in the hexadecimal. For the first group 0001, the equivalent hexadecimal will be equal to 1, and for the second group 1001, the equivalent hexadecimal will be equal to 9. So it will be equal to 91 in hexadecimal. We can also find its equivalent in octal. 100100001 could be converted into octal as well. For octal, the groups that we will make will contain 3 digits. So 001 will be equal to 1. 010 will be represented by 2. And here we have 2 digits. We can add a 0 to the left side. 010 will be also represented by 2. So 2, 2, 1 in base 8. And you should also see something here. Yeah? If you consider these two examples together, you should see a way of converting from base 8 to base 16 using the intermediate base of 2. So we can convert from base 8 to base 16 and vice versa quite easily if you use the base 2 as the intermediate step. It will be easier than doing the direct conversion or using the decimal as the intermediate step. So here is written what I meant. In order to convert from octal to hexadecimal and vice versa via binary, we need to convert the octal to the binary, then use groups of 4 bits and convert, as we did in the example, into the hexadecimal digits. Let's go through this example. So we have 635 point, this is the radix point, 177 in the octal, and we want to find its equivalent in the hexadecimal. For each digit in the octal or in base 8, we will use 3 digits in the binary. So we will use the intermediate step or intermediate base of 2. For 5, we will have 101. For 3, we will have 011. And for 6, we will have 110. And similarly, for the digits on the fraction part, we will have 001, 111, and 111. So this is what we have in binary. And then in order to convert this into the equivalent hexadecimal, we would need to create groups of 4 bits. For the fraction part, for the integer part, we start with the rightmost bit or digit. We create this group here, and then another group of 4 bits, and another group of 4 bits. For the leftmost hand one, we have a single digit, so we can append indeed 3 zeros to its left side because the value of the number will not change. And then find the equivalent values here. So 1101 is representing us 8 plus 4 plus 1, which is 13. A, B, C. So this gives us C. No, D indeed. 13 will be represented by D. A is 10. So A is 10, B is 11, C is 12, and D is 13. So we will have D here. For 1001, we have 9, and for 0001, we will have 1. So 19D dot. For the fraction part, we will start from the leftmost digit and create groups of 4 digits. For the rightmost one, we have a single digit, so we can append in the 3 zeros to its right side, because for the fraction part, we can add as many number of zeros that you want. The value of the number will not change. And then we just find their equivalent in the hexadecimal. 0011 will give us 3, 1111 will give us F, and 1000 will give us 8. So we will have 3F8. And as a result, we have found the equivalent of 635.177 in octal in the hexadecimal. And you can see how using the binary or base 2 as the intermediate base eases the indeed process of converting from octal to hexadecimal and vice versa. If you wanted to do this directly, it would be quite a lot of work, or you could alternatively use base 10 instead of base 2, but that would be also more difficult or more time consuming than using the binary as the intermediate step. Alright, so here for the base conversion, you can see the positive powers of 2. Just to make it easier for you to do the conversion, if the exponent is equal to 0, for 2 to the power of, you can say that here we have I, and here we have 2 to the power of I expressed in the decimal form. So 2 to the power of 0 will be equal to 1, 2 to the power of 1 will be equal to 2, and so on and so forth. So this table is only presented here, provided here in order to give you an idea of what will be the equivalent number for the decimal equivalent of the exponential in base 2. So 2 to the power of 21, for example, is shown here. 2 to the power of 20 is shown here, and so on and so forth. So sometimes it could be useful in order to have a quick look at this kind of tables. Alright, so I think that's all for this video. Thank you for watching, and see you in the next video later. Bye for now.